Hi everybody, welcome back. So today we're going to talk about Kepler's laws. Now, Johannes Kepler lived in the 1600s and he was the epitome of the shy geek. I mean, if he lived today, he'd be wearing horn-rimmed glasses and he'd have tape right in the middle. But he was a genius when it came to looking at patterns and numbers. And if you've ever seen the movie A Beautiful Mind, the character could just look at these patterns and numbers and see relationships. That's what Kepler could do. Kepler did his work before telescopes were invented. He did his work before gravity had been discovered. So these patterns that he saw in the data of observations of the solar system have now become basically the three laws that govern all of modern astronomy. So it's one of the most important things that we'll talk about here. So let's take a look at each one of his laws. The primary one you're going to be using is going to be the third law, but you need to understand the first two so that you can get there, okay? Let's get started. All right, so starting out with Kepler's first law. So when Kepler was looking at the data, now prior to Kepler's time, basically we assumed that all the planets moved in a circle. The heavens were from God, the only perfect form is a circle, so therefore the planets must be moving in a circle. And Kepler just about had a nervous breakdown, literally, trying to fit the data to this circle. Finally, he eventually said, I just can't do it. It's not going to be a circle. And so this then was the form of his first law. And I've highlighted kind of the two most important parts here. So first of all, each planet's orbit is around the sun is an ellipse, not a circle, with the sun at one focus. And what that means is that it's not in the center of the orbit. It's actually off to the side at one focus. And we'll talk about what that is here. So if we draw a picture of the orbit, so we're going to have the sun here. And here is our orbit. So an ellipse is just an oval. That's the technical term for an oval. And you notice that we've got a long axis here and a short axis here. So that here's the center of the orbit, and the sun is actually not at the center. It's off to one side. We call that a focus. And one trick you can do if you ever need to draw a great big oval for a sign or something like that is take two thumbtacks and stick it into the cardboard, and then drape a loop of string around those thumbtacks and stretch it tight with a pen. And then as you draw, you'll draw a nice perfect oval every time. So it's a neat little trick. Well, those points where you put the thumbtacks, that's the foci. That's foci is the plural of focus. There are actually two focuses in there. There is nothing at the other focus in our solar system. There's no planet X, no doomsday star, nothing like that. It's just empty space. But our sun is at one of the focus. And if you want to call it focuses, hey, I'm from Tennessee, it's fine with me. So the orbit of the planet then comes around like this. Now, looking at this long axis here, we call that the major axis. The minor axis we're not going to spend a whole lot of time with. If you ever learn about flying spacecraft and orbital mechanics and things like that, we'll use that. But for our class, pretty much we're only interested in this long axis. Half of that major axis is called the semi-major axis. Semi means half. So when you were in preschool, if you ever sat in a semicircle, you were sitting in half of a circle. If you go get a checkup at your doctor every 6 months, that's a semi-annual checkup. So semi means half. You've run into that before. So semi-major axis is half of the major axis. What it is the average distance of the planet to the star. So we can think about this as being the size of the orbit. And pretty much everything we do in this class is going to be, when we talk about the size of the orbit, we're going to be talking about the semi-major axis of it. We generally measure this in our solar system. We generally measure this in astronomical units. 1 AU is the distance from the Earth to the sun, the average distance from the Earth to the sun. Now, because it's not a circle, the planet is closer at some points than it is at others. This point where it's closest is called the perihelion. Para means close, helios means sun. So para, you've probably seen this, like if you're about to have a baby, then you're put in the perinatal ward. If you've got gum disease that's right next to your teeth, then it's called periodontal disease, things like that. Para means close. So perihelion then is where the planet is closest to the sun. Aphelion is where the planet is farthest from the sun. Apos means far, helios of course means sun. So if the orbit were a circle, the planet would be the same distance all the time from the star. Instead, because it is an ellipse and because the sun is not in the center of the orbit, sometimes the planet is closer to the star, sometimes it's farther away. So for each of these laws, I want you to know some definitions here, know the definitions that we've talked about, but then know how the law is stated, but then I'll also kind of give you Kilo's definition. I'll give you how it's actually used. So in this case then, The key is that it orbits in an ellipse with the sun at one focus. So it's not a circle and the sun's not in the center. So the key fact with that is that planets are going to be closer to the sun at perihelion and of course farther away at aphelion. So that's what these two things, these two parts of Kepler's law says. So Kepler's second law is the one actually people have the most trouble with, so we're going to spend a little bit of time with that. Here's how it's stated. And how it's stated is not quite how it's used, but it leads to how it's used. So let's kind of work through that. The planet's speed changes in such a way that it sweeps out equal areas in equal times. Let's see what we mean. So here's our orbit going around the star. Now imagine I have a point A here. And that's, let's say my planet is there. So a line, when it says it sweeps out an orbit, we draw a line from the star to the planet. Then here's point B. So do you see, if you think about it as like if you took a ruler and dipped it in paint and then painted this area. So as it travels from A to B, it travels along the black line, but then it sweeps out this whole area inside here that you see. So what Kepler's second law says is that if the areas are the same, then the times are the same. So let's take another area. Let's say I've got one here at C. So we draw that line. And then here's D. We'll draw that line and then we'll color in the area. So what I'm claiming, and as close as I can get it with my limited ability to draw in PowerPoint here, is that this area is equal to this area. Let's see if you can agree with that. This one's short, but it's fat. This one's long, but it's skinny. So one way you can think about it is that it would take the same amount of paint to cover this as it would to cover that. And if you'll buy that, that's what I'm shooting for anyway. So the areas that are swept out here are the same. Here's what Kepler's second law is saying. It's saying that since the areas are the same, the time from A to B is the same as the time from C to D. Okay, so since these areas are the same, and we're claiming they are, then the time to travel along this black line from A to B is the same as the time required to travel along the black line from C to D. So let's analyze that. So where does the planet travel further? And by that we mean along its black line. Does it travel further from A to B, from C to D, or is it the same amount of distance that it travels? And we're looking at this diagram here. Pause the video and answer the question. Okay, so we want to know, where does it travel further? Does it travel further from A to B, or does it travel from C to D? Well, obviously it's going to travel further from C to D, and you can see that on your chart here. It's a longer line. That's further it's got to go. All right, so the time between the points, though, this is using Kepler's second law. Those areas are the same. What does Kepler's law say about the time between A and B and C and D? Pause the video, think about it. Okay, well now there's no reason why it should be. Kepler just noticed that it is. And we're going to talk about why it should be because we now understand how gravity works. Kepler just saw this pattern in the data. And he said, okay, well, if those areas are the same, then the times are the same. And so in this case, since those two areas are the same, the time is going to be the same as well. Here's the key then. If the planet is traveling further from C to D in the same amount of time as it travels from A to B, where is the planet traveling the fastest? From A to B, C to D, or it travels the same speed no matter what? Pause the video and think about it. So let's give you an example. Let's say that you and I are driving to Flagstaff, and after an hour, you've reached the turnoff to Prescott, for example. Let's say that after an hour, I've traveled all the way to Flagstaff. So we traveled the same amount of time, but I went a much greater distance. Who's moving faster, you or me? Well, I am by a whole lot, as in, don't drive with this guy if he can make it to Flagstaff in an hour from Phoenix. So because the planet travels a greater distance in the same amount of time, it must be moving faster from C to D. So this then is the key to what Kepler says. It has, if there are equal areas, then they're equal times. But the key fact with that is the planets move fastest at perihelion. Okay? So let's look at that right here. So right here is perihelion. It's moving fastest as it goes around that way. All right, so let's look at the third law then. Oh, I'm sorry. Before we get into the third law, I was going to explain why this actually works. And if you look on the back of your class notes, you'll see that. If I take, this pen and I throw it up into the air, it's going to go, as it moves away from the Earth, which is its gravity source, it's going to go slower and slower and slower. Eventually it's going to stop, and then it's going to start to fall. What's going to happen to its speed as it starts to fall back towards the Earth? It's going to go faster and faster and faster. Well, the same thing is happening with the planets. So imagine that, here's my gravity source, that's the sun. So imagine this planet goes up like this. It's going slower and slower and slower and slower. You can kind of think about turning it sideways if you want to think about it falling towards it. But then when it gets up here, it starts to turn back towards the sun and it starts going faster and faster and faster. Well, that's just because it's falling into the sun. The difference between a planet and the pen, is it's falling faster and faster and faster, but it misses. And so right here, it's moving as fast as it's going to go, and now it starts slowing down again. Until now it's as slow as it's going to go, and then it starts going faster and faster and faster. So the Earth has been trying to fall into the sun for 4.5 billion years. It's just missed every single year. The universe is actively trying to kill you. It's just not a very good shot. All right, so let's look at Kepler's third law then. Kepler's third law is almost always written in math. There's no real reason to think about the definition of it because the definition of it is nothing more than the math. The cube of the semi-major axis of the planet's orbit is directly proportional to the square of its orbital period. What that means is this, that the cube of the semi-major axis, remember that's the size of the orbit, is equal to some constant because they're directly proportional. Remember, thumbs up in the same direction. The p is the orbital period squared. So you do need to keep up with the units for this. Now, Kepler didn't know what that constant was because, as far as he knew, there was only one solar system that existed out there. As we've looked at with gravity, we now know what that constant is. So A is the semi-major axis, P is the orbital period. We measure A in astronomical units, remember. So for example, the Earth is 1 astronomical unit. Mars is 1.5 astronomical units. Jupiter is a little over 5 astronomical units. Mercury is about 0.4 astronomical units because it's closer. The orbital period has to be measured in years, and that's Earth years. So if for some reason you measure it in days, you just divide by 365, and that's going to convert it to years. So Mars, for example, might be around 1.8 years, something like that. Now, now that we understand gravity, we now know that that constant is actually the mass of the central object. In the case of the solar system, that's the sun. But we use the same equation when we're flying spacecraft around the Earth. In that case, the mass is the Earth. So it's whatever's in the center. It's going to be real important when we start talking about binary stars in the next lecture. But whatever happens to be in the center, that's going to be this mass. For the solar system, it's the sun. So M is the mass of the central object, and we measure that in solar masses. So the sun is 1 solar mass. If it's twice the size of the sun, it's 2 solar masses, and so on. Now, Kepler's third law will allow us to find if I give you any of the two, you can find the third one. So if I need to find the semi-major axis then I just use the straight up form of Kepler's third law, but I need to get rid of that cubed. So I'm going to take the cube root of both sides, like that. Now you might have a cube root button on your calculator, you might not. If you do, you could put in m times p squared. Now it's not mp squared. Make sure only the p is squared. That's a common place that people start to mess up. So mp squared. And then hit equals and then use your cube root button. If you don't have a cube root button, and my calculator, for example, does not have a cube root button on it, what you can do is you can raise it to the 1/3 power. Now, I don't like doing fractions in here, so what I usually do is I take m times p squared, you probably have an x squared button on there, hit equals, and then use your either caret, the little up, or y to the x, depends on your calculator, and then raise it to the 0.3333333333333 until you get board power. And that'll give you the right answer pretty much every time, okay? So if I need to find the semi-major axis, I need the mass of the central object and I need the orbital period. In your practice, you're going to be doing all three different things. So if I know the semi-major axis and I know the mass, I can find the orbital period. So we'll start with Kepler's third law then, and we're going to solve this for p. So the first thing I need to do is get that m to the other side. Well, it's multiplied, so we're going to divide both sides by m. And I'm left with this. Now I need to get rid of the square, so I'm going to take the square root of both sides. And this is the final form. So if I know the semi-major axis, I just cube it. And again, depends on your calculator. That might be a caret and a 3. It might be x to the y 3 or y to the x 3. If you have any problems, just come into live help and show me your calculator on the camera, and I'll show you what it is that you need to hit for that. This is what we're actually going to be using on Thursday. We're going to know the semi-major axis, and we're going to know the period. We need to find the mass of the central object. So we're going to divide both sides by p. And here then is how we find the mass of the central object. You just measure the semi-major axis of it, measure the period, cube and square it, divide it, and you've got the mass. This is how we find the mass of things in the solar system and actually anywhere in space. We generally have to, if we're trying to find the mass of a planet, we have to use a moon. And for example, with Venus and Mercury, that doesn't have any moons. So we didn't know for sure what their mass was until we sent a spacecraft there. When we got the spacecraft in orbit, then we could say, okay, I know what the semi-major axis of that orbit is, and I know what its period is. I now know the mass of the planet. So that's how we were able to do this. We can also use this to find the mass of stars if I can actually see a planet going around it. But other than our own solar system, that's actually pretty hard to do. Okay, so look on your class notes, and we've got some samples here that we're going to work together. So the first one gives you a mass of 1.0 solar masses and a semi-major axis of 1.52 AU. And then we want to find the period. So which of these three do we want to use? Well, to find the orbital period, we're going to use the second one. So we need to find a cubed divided by m. So let's see if I can get my pen to write on this. So this means that it's going to be the square root. A is 1.52, and then we need to cube that. And here the mass is just 1. So when I put that into my calculator, I get 1.52 raised to the third, and I get 3.51. I need to divide by 1. Of course, that's not going to change anything. And then finally take the square root, and I am getting 1.87. And that's 1.87 years. And it turns out this is Mars. Okay. So pause the video, make sure that you've got that one. Make sure that you can do it. For this one, I want you to pause the video first, and let's see if you can do it. So we've got 1.75 solar masses, and the period is 3.56 years. We want you to figure out the semi-major axis of the orbit. How far away is the planet from the star? So pause the video, figure out which of these three cases you're going to use, and then do the math. Okay, hopefully you did that and you didn't just wait for me to do it with you. But let's do it together. All right, so in this case, I want to find the semi-major axis. So I'm going to use the third one that you see here. And I'll just have to write it up here. So the mass then is going to be 1.75 times the period, which is 3.56, and we need to square that, and then we're going to raise it to the 0.33333333 until you get board power. So 1.75 times 3.56, and then hit your x squared button. Make sure that you don't hit equals in between. When I just square the 3.56, I get 12.67. When I multiply that by the 1.75, I get 22.18. See if you get the same thing. And then the last step is to raise it to the 0.33333333 power. So on mine, it's y to the x. And I'll raise to the 0.3333333333. Okay, I'm bored. And I'll hit equals, and I get 2.81 AU. So again, find my pen. I'm getting 2.81 astronomical units. So 2.8 times the distance from the Earth to the Sun. So somewhere between Mars and Jupiter. All right, for the last one then, we're going to find the mass. Now, this is what we're actually going to do in the next lecture. This is going to be the most important form of Kepler's third law that we're going to use. We're going to find the semi-major axis and the period of a binary star system, and you're going to figure out the total mass of that system, because in the case of a binary star, the total mass is the two stars that are there. So in this case, then, we're telling you that the semi-major axis is 0.75. We're telling you that the period is 2.14. Plug that in. Let's see if you can get it. All right. So let's do it down here. So this is going to be 0.75 cubed divided by 2.14 squared. So the 0.75 raised to the third, I get 0.422 divide by 2.14 squared, and I get 0.0921 solar masses. 0.0921 solar masses. Okay, see if you get the same thing. If not, go back, figure out what's going on, or come to live help and I can walk you through it. All right, that's it for this one. The practice has a section on each of the three laws. You'll be doing basically the same kinds of things that we've been talking about here. So make sure you've got that, get it scanned, and send it up. You'll be good to go. Okay, so now you know how to use Kepler's laws, and which you use depends upon what you want to get out of it. It's the same equation. We've just solved for the different letters that are in there. You'll always have at least two, and then you'll find the third from that. One little tip to remember: that if we're in the solar system, the mass of the central object is the sun, so the sun is one solar mass. So m will always be 1 if you're working with something in the solar system. On the other hand, in most cases, though, it's not going to be exactly 1. It'll be something a little bit different. But here again, the most important thing that we're going to be using out of this then is to find the mass of an object. And that's what we're going to be working with next time when we start talking about binary stars. We'll see you then.